Hello my scholars, you're welcome to Myschool YouTube channel. My name is Emmanuel and in today's video we'll be tackling JAMB past questions in chemistry for year 2001. Please stay with us, don't go anywhere, we'll be right back. You're welcome back to my school YouTube channel. In today's video, we'll be tackling questions 26 to 50. Let's now get down to question 26. When delta H is negative, a reaction is said to be what? When we talk about delta H, we're talking about change in enthalpy, okay? And that is the amount of heat actually that is involved in the reaction for it to take place. So if delta H is negative, it means that the reaction is actually exothermic because heat is actually evolved, okay, into the environment, from the system into the environment. So it means that a reaction is said to be ionic, no. Reversible, no, it's not reversible. If it is, it will not be negative. Exothermic, okay, and then we have endothermic. It would have been endothermic if delta H were positive, because it would have been that heat is absorbed into the system. But in this case now, delta H is negative. It means heat is what is given off, or it's evolved into the environment. And in that case, it means that delta H is negative, implies that it is an exothermic reaction. So option C, exothermic, is the correct answer. Now question number 27. As the concentration of an electrolyte reduces, the conductivity does what? Does it reduce to zero? Does it decrease? Does it increase? Or is it unaffected? Now, the more the concentration, or the higher the concentration of a solution, the higher the conductivity of that solution too. The reason being that the number of ions, okay, that make up that electrolyte or that make up the solution will also increase. So in other words, it is directly proportional, okay? Concentration of the electrolyte is directly proportional to the conductivity of the particular. The reason being that as the number of ions increases, okay, conductivity will also increase. The activity will increase there. So if concentration increases, what happens? The conductivity increases as well. But if concentration decreases or reduces, then the conductivity will also reduce and get decreased. So the question says, as the concentration of the electrolyte decreases, okay, the conductivity will also decrease or reduce. Option A say reduces to zero. No, because we still have the ions present there, so the conductivity cannot be reduced to zero. Decreases, yes, it will decrease because concentration is decreasing, okay, reduces, then conductivity will also reduce or decrease. It is not increasing, it is not unaffected. It is that as concentration of the electrolyte reduces, the conductivity will also drop, okay, it will also decrease. So because of that, the correct answer is option B, decreases. Now question number 28. In which of the following reactions has the oxidation number of nitrogen increased? So all of these options here, we have option A, NO. We want to calculate the oxidation number of nitrogen in this NO, and then we compare with the one we have on the right hand side. If there's going to be an increase, you do same for all of them, okay? So but bear in mind that option A, NOBr, okay, actually has this Br. Of course, bromine should have been -1, okay, that is the oxidation number of bromine on its own if it is bromide ion, okay, but because it is combined with oxygen, so it has as hypobromite, okay, hypobromite. So in this point now, oxygen will still be -2, but bromine will no longer be -1, it will now be +1. So that's the oxidation state of bromine or bromide ion in hypobromite will be +1. So the same thing is applicable to this, okay, NOCO. So this is hypochlorite ion. In hypochlorite ion, the oxidation state of chlorine here will be +1, +1, not -1 if it were to be a chloride ion, okay. So bear that in mind. So now let's move to the board now to see what happens in this. For this, oxidation number of NO, of course, NO is common to all the options that we have. Option A, B, C, D, we have it on the left hand side. So nitrogen, NO equals to 0, so that N plus oxygen is -2. We have that there, equal to 0. So N positive multiplied by negative, that's -2 equal to 0. So N is equal to +2. So which means for all of nitrogen in NO in all the options, it is actually +2. So all we need to do now is let's go to the right hand side, the product side, where we have all the, that's where the variation is actually. So for the first option A, we have NOBr as one of the, as the product. Okay, so we can calculate nitrogen is N plus oxygen is -2, then plus bromine is +1. I said that earlier on, that bromine in hypobromite, okay, is +1, not -1, as if it were on its own. So, okay, so this is +1 equal to 0. So N plus -2 plus times this gives us +1 equals to 0. So by the time you solve this one, we have N equals to +1. Okay, so for option B, we have NO2. Okay, that's what we have on the product side. One of the product, okay, the product we have on the right hand side. So by the time you have that, we have nitrogen plus, this is -2 times 2, because we have 2 of this, equal to 0. So N, that will be -4 equal to 0. So N is equal to +4. Okay, for option B. Option C, we have FeNOSO4. Okay, so we don't know if this Fe is ion 2 or ion 3, but we can know that from the radical. If you take SO4 as radical, is actually 2-, okay, and then this NO, if you take it as a radical, that should be -1. It's -1, and this is -2. Okay, so -2, -1, that will be -3, -3. So we also need 3 positive, okay, ions to be able to what, to combine with this. So Fe definitely will be +3, since this one is the combination of the two anions are actually -3. So this one should be +3. So ion 3 plus nitrogen is there. Then we have plus oxygen is -2. Then plus the whole of this, we can just take the whole of this radical to be -2. Okay, so we have -2 here equal to that, so that we don't waste much time. So this is +3 plus N, -2 here, -2 here. That gives us -4. Okay, so equal to 0. So -3 plus 3 minus 4 is -1 plus N. So N is equal to +1. And the last option here is option D. We have NOCl, okay, on the right hand side for the reactant. So we have N here plus oxygen is -2 plus chlorine, okay, here will be +1. It should have been -1, but because it is forming hypochlorite, okay, here with oxygen, so the oxidation number is now +1. So we have +1 here. So -2 plus 1 gives us -1 equal to 0. So N is equal to, of course, that will be -1. So the question says that in which of the following reactions has the oxidation number of nitrogen increased? So we are going to compare this to all of the options now. From +2 to +1, of course, that is a reduction. So it reduces, okay, that decreases, yeah? Decreases. Then option B, NO2. So we have NO2. Compare this to NO2, where we have +2 to +4. Of course, that is an increase. So it increases here. Then for this, nitrogen here to this, from +2 to +1. Of course, that is what, a decrease. Okay, so it decreases there. And the last option is with NOCl. Okay, so if you look at that, from +2 to +1, of course, you agree that that is also what, a decrease. So among all of this now, it is option B, that is where we have an increase. So let's move back to the screen and let's see what we have. So for this, we have the oxidation state is changing from +2 here to +1, from +2 here to +4, from +2 here to +1, from +2 here to +1 also. So the only place where we have an increase in the oxidation number or oxidation state of nitrogen being increased is option B. So that is the correct answer. Question number 29. NH3 ammonia gas, take note of that, react with HCl gas. Okay, this is not hydrogen chloride. This is not hydrochloric acid. This is hydrogen chloride because it's in gaseous state. If it were aqueous, it would have been hydrochloric acid. Okay, so this is ammonia gas reacts with hydrogen chloride gas to give us ammonium chloride solid. So you can see here that gases react with themselves to form what? Solid. So that is what we call a deposition. When a gaseous substance changes form to solid substance, it becomes what? Deposition. If it is a solid that is changing to gas, okay, it becomes what? Sublimation. Okay, so in this case now, gaseous substances are changing to what? They react together to form a solid substance. So deposition takes place. So in deposition, the question says the entropy change in the system above is what? Is it negative? Is it indeterminate? Is it positive? Is it zero? In the section where we have this, don't forget gaseous substance are changing to solid substance. So which means that the level of entropy in gases, of course, is actually higher than what? Than when it is in solid, because the particles of solids are packed together, closely packed together. So you have less number of what? Of entropy value, a lower value of entropy change in solids compared to this, because don't forget that entropy is actually the degree, a measure of the degree of disorderliness, okay, in the system of that particular substance. So we have more disorderliness in gaseous substance because the molecules are always colliding with each other and then at random moving on a perfectly elastic collision taking place in that point. So the level of disorderliness is higher in gaseous substance than it is in solid substances. So because of that, we are having a deposition from gaseous to what? To this. So entropy is higher here, okay, and then it is lower in this point. So there's a decrease. So eventually you are going to have a negative value of entropy change, because the entropy change in the system above is going to be what? Is going to be what? Negative. If it was the other way around, if we had this on this side and then we have this on this side, so changing from solid to what? To gaseous, because the gaseous substance actually will be having a higher value. So that means we are going to have the entropy value will be positive. But in this case now, we are moving from higher to a lower. Okay, so it's going to be a negative. So not indeterminate, not positive, not zero. The answer is negative. Option A is the correct answer. Question 30. Fermentation is the what? If you know the definition of fermentation, then you can be able to answer this question without an issue. It says breaking down of carbohydrate to glucose, conversion of sugar to alcohol in the presence of yeast, breaking down of sugar to carbohydrate, conversion of alcohol to sugar in the presence of yeast. Of course, option, you can use the elimination method, okay? Fermentation process actually has to do with a conversion of sugar, okay, into alcohol, okay. It ferments. Of course, the word ferment is not a big grammar, okay. We have sugar fermenting, okay. Once it ferments, okay, we have it, or we have fruit. Some fruit ferments. Once they ferment, what happens? They turn to what? Alcohol, okay. So the process through which sugar is converted, when we say sugar, sugar could be your glucose, could be your fructose, it could be the disaccharides. When we talk of sucrose, talk of lactose, talk of maltose, okay, and so on. So when the sugar, okay, now is converted from what it is into alcohol, okay, it ferments. But that will not take place without the presence of a microorganism. That's what makes it ferment. Microorganism. And the microorganism here we're talking about is yeast, okay. So option A says breaking down of carbohydrates to glucose. No, that is not fermentation. If a large molecule is broken down into smaller molecule, okay, that could be cracking, okay. In petroleum we talk about cracking, okay. Then in this case we have so it is not option A. Look at option B, breaking down of sugar to what? To carbohydrate. You can't break sugar down to carbohydrate because sugar is like the end product, like the smaller unit. Like glucose now is a sugar, okay, of what? Carbohydrate is a macro molecule, it's a bigger molecule, okay. So you don't break a smaller to something that is bigger, okay. Option D, conversion of alcohol to. So option B and D looks alike, okay. Of course, we've taken out option A, we've eliminated option C, so it is between option B and option D. And from the definition that I gave about fermentation, that fermentation has to do with a breaking down of sugar, okay, into alcohol, okay. Of course, CO2 gas is also formed there. So once that happens, it must happen in the presence of what? Of yeast. So option B says conversion of sugar to alcohol in the presence of yeast. Correct. Conversion of alcohol to sugar in the presence of yeast. This is not correct. So option B, conversion of sugar to alcohol in the presence of yeast, which is the microorganism, is the correct answer. Question number 31. The general formula for the alkanals is what? General formula for the alkanals. Alkanals generally have this formula, CnH2n plus 1, okay, and then we have CHO. This is the functional group that makes it, that qualifies it to be alkanal. Option A says ROH. Of course, OH here is functional group that is associated with what? Alkanols, okay. Alkanols, your alcohol, ethanol, methanol, they all fall underneath it because of the OH. Now we have R2CO, okay. This CO here is ketone, okay. Ketone actually have this, functional group CO, okay. Here we can have it, it can be RCOR, as you want to have it, RCOR, okay. So that is functional group for ketone, so this is not it. We have RCOOR prime, okay. So this is meaning that these are alkyl group. This could be CH3 and this is CH2, CH3 or CH3, as the case may be, okay. And then we have this, so this one as COO here is what actually makes this to be an ester, or what we call alkanoate. We call them esters, we call them alkanoate. They undergo esterification, okay. So these are esters, okay. So this is not correct. This is the functional group for ester, general formula for this. This is the aldehyde. Now the aldehyde, the alkanal that we have, this RCHO, that's the alkanal CHO. So you can see the CHO here, the functional group that goes with it. So the correct answer here is option D. Question 32. The main impurity in iron ore during the extraction of iron is what? Iron ore actually is, iron is gotten from iron ore, okay, when you extract it. But during the extractions, we have impurities that are there. So many of them, because it is found as ore, okay, in an impure state, okay. So, but the greatest among, or the one that has the larger percentage of the impurity is actually silicon dioxide. That is why usually we talk about, of course, you get this in the soil, okay, and then what you have a lot of sand, okay. Yes, that is present, and that is silicon dioxide, SiO2. That's the formula for sand that is formed. So how do we remove that impurity? When you add calcium oxide to it, okay, calcium oxide added to this, okay, let's look at the screen. Calcium oxide added to, this is your impurity in the iron ore, silicon dioxide react with calcium oxide, okay. We have SCA, Si, we have O2, that is O3, okay. Then this one will be removed eventually. This is serving as the acid, okay, while this one serves as the base. It's a neutralization reaction. So once it happens there, we have a salt there. So in other words, the main impurity in iron ore during the extraction of iron is silicon 4 oxide, or what we call silicon dioxide, not carbon 4 oxide, not calcium triiosilicate, not sulfur 2 oxide. The correct answer is option A. Question number 33. During the vulcanization of rubber, sulfur is added to do what? Why we add sulfur during vulcanization of rubber is just to improve on the strength, okay, of that particular rubber. We want to increase the strength, the chemical reactivity, the strength of that particular rubber. We want to strengthen it, okay, to increase the durability, and so on. So we add sulfur into it. So when we do that, what are we doing? We are only trying to do what? To put the molecules of that rubber together, okay. So we are not, option A says break down rubber polymer. We are not breaking down any polymer. We want to increase the strength of something. That means you are adding something up to make it stronger, okay. So you can't be breaking down rubber polymer. Then lengthen the chain of rubber. Lengthening the chain of rubber is not, the reason why we have, if we want to lengthen this chain of rubber, then we should get more monomer, okay, that actually make up that rubber to what? To lengthen the chain of that rubber, okay. The option C says bind rubber molecules together. The molecules of rubber, you bring them together so that they can be stronger and harder in terms of strength, okay. So option C is correct. Option D says act as a catalyst. No, it's not acting. It's not trying to speed up the rate at which that rubber, is produced. But the correct answer here is to bind rubber molecules together. During vulcanization of rubber, sulfur is added to bind rubber molecules together in order to increase the strength of the rubber. So the correct answer is option C. Question 34. Catalytic hydrogenation of benzene produces what? Hydrogenation reaction has to do with addition of hydrogen, okay, hydrogen molecule, but it takes place in the presence of a catalyst, okay. So what does it produce? Benzene, on the other hand, don't forget, is an aromatic compound, okay. It has conjugated, of course, you can say it has some conjugation in between. There are double bond, single bond, single bonds, okay. We have some double bonds in between, about 3 of that. So let's move to the board so we can see what happens here, okay. Benzene has the formula C6H6, okay, reacting with 3 moles of hydrogen molecule. Why do we have 3 moles of hydrogen? Because we need to break down, this is the structure of benzene. We want to break off these double bonds that we have here. We want to break them off so that we can have hydrogen come in. That's the only time hydrogen can come in. If these bonds are not broken, nothing can happen here. So for this reaction to take place now, initially we have, don't forget, at each of these points we have carbon, and with 1 hydrogen. That's why we have C6H6. So when you react this with this, we have this. Ordinarily, there should be an intermediate product, okay. First, we will form, of course, each of the double bond will be broken off first. We will form a cyclohexane first, okay, but the reaction will continue to completion till we have that double bond broken off. We have C here, carbon here, carbon here, carbon here, carbon here, okay, and then we have hydrogen reacting to H2, so that eventually the double bond that is here is off, and then 1 hydrogen comes here and another comes here. This double bond is broken, we have 1 here, 1 here. This double bond is broken, we have 1 hydrogen here, 1 hydrogen here. Eventually we are going to have C6H12, okay. It is 1, 2, 3. How many carbons do we have? We have about 6 of that, so that is X, of course, for an alkane, hexane, because it is in cyclic form, so we call it cyclo, okay, cyclohexane. Cyclohexane is what we have. So catalytic hydrogenation of benzene will always give us cyclohexane, not hexane. Let's move to the screen and see what we have. Option A says it is oil. No. Option B says it is cyclohexane. No. Looks like this. Option C says it is cyclohexane. And option D says it is margarine. Of course, the answer, it would have been margarine if it is said that the adenine, okay, the adenine of oil, fat and oil, okay, will give us margarine, okay. But the catalytic hydrogenation of benzene is actually cyclohexane, option C. Question number 35. A trihydric alkanol is, what is a trihydric alkanol? Tri means 3, okay. When we have a carbon atom, we have hydroxyl group, that's the OH, attached to different carbon atoms, okay. It is tri when it is 3. We have 3 OH attaching to carbon atoms. If it is 2, it would have been dihydric, okay. If it is 1, it will be monohydric, okay. We can have polyhydric, you can have more than 3, 4, and so on and so forth. So a trihydric alkanol is what? Is a carbon atom, okay, that is of an hydrocarbon that has OH attached, about 3 of them attached to it. Glycerol, of course, is most likely the correct answer. Phenol is just a benzene ring with OH attached to it, okay. So glycol is also not that, and then we have ethanol. Ethanol is also, even though they all have OH attached to them, okay, just like ethanol has OH, ethanol is your C2H5OH attached to it, but we are talking about trihydric, okay. This is just 1 OH attached, 1 OH attached, 1 OH attached, but this one has 3 OH attached to it. If you want to draw the compound of this, we can draw it. Let's see, glycerol, that is actually propane 1, 2, 3 triol. So we have a CH here, 2, we have a bonded to CH, then we have CH2. So here is OH attached to it. Okay, this should be this way because oxygen has double bond. There's 2 bonds, OH and then HO. So this is 1, 2, 3. That's 3. The IUPAC name is propane or propan. OH, OH, OH. 1 on carbon 1, carbon 2, and carbon 3. So we have 3 of them, triol. So in other words, propan 1, 2, 3 triol is also referred to as glycerol. Propan 1, 2, 3 triol. So a trihydric alkanol, let's move to the screen, is glycerol. Option A is the correct answer. Question number 36. When chlorine is passed into water and the resulting solution exposed to sunlight, okay, the sunlight is what is going to provide the energy that will be used in the reaction, okay, or the ultraviolet light from the sunlight, okay. Resulting solution exposed to sunlight, the product formed are what? Is it chlorine gas and hydrogen, oxygen and oxochlorate 1 acid, this and this. So what happens is the reaction is between chlorine and water, okay. Of course, if sunlight were not there, we shouldn't have had HCl. What we would have just had was just that would have been hypochlorite, okay. But first of all, something happens first. Hypochlorous acid will be formed first when chlorine reacts with water, okay. We form hypochlorous acid. Then the hypochlorous acid is now broken down eventually into hydrochloric acid and oxygen gas. So let's move to the board. Let's see what we have. So first, what happens is we have Cl2 react with H2O, okay, react with H2O to form the hypochlorite, okay, hypochlorous acid. Then hypochlorous eventually breaks down into HCl and oxygen gas will be produced. We can have 2 moles of this. We have 2 of this. Of course, you can balance up the equation eventually, and then we have so. But our area of concentration is what? These are the products that we have. But don't forget, this takes place in the presence of UV light. Okay, actually from the what? From the sunlight. That is what gives the energy, that provides the energy that is needed for this reaction to actually take place. So the end product is actually hydrochloric acid and what? Oxygen gas. Let's move back to the screen and see what we have. Okay, the only place we have hydrogen, not this, where we have hydrochloric acid and oxygen gas. Okay, that is option D. So the correct answer here is when water reacts with chlorine in the presence of sunlight, passed under sunlight, the product is usually hydrochloric acid and oxygen gas. Option D is the correct answer. Question number 37. Proteins in acid solution undergo what kind of reaction? Is it polymerization? Is it substitution reaction? Is it fermentation reaction? Is it hydrolysis? Okay, it should have been polymerization if we have several protein, but protein is a macromolecule on its own. Okay, so it is, you can't have protein combining together to form another compound. Okay, if you want to have that, then it should have been polymerization. If you have several protein, okay, combining together to form a larger molecule or a larger compound, then we have polymerization. But this is reaction between what? Protein and acid, okay. And then we have a substitution reaction. If the acid is going to substitute, maybe the hydrogen is going to get substituted into the protein. Of course, the end product of protein is actually amino acids, and the amino acids are actually linked together by what we call peptide bonds. So the peptide bond, the essence of this acid reacting with this protein is to break those peptide bonds, okay, that hold the amino acids, several monomers of amino acids together, so that you can have, you know, smaller units of amino acid. So protein will react in a concentrated acid in a reaction that is called hydrolysis, because that hydrogen ion that is there will definitely come in now to do what? To break down the peptide bond that we have present in the protein. So protein in acid solution undergoes hydrolysis reaction, not fermentation reaction. Remember, we said fermentation reaction has to do with, you know, conversion of sugar into alcohol in the presence of yeast, okay, but that is not the case here, okay. And it's not substitution reaction because an element is not replacing another atom of element in that protein, okay. So it is not substitution, it's not polymerization, it's not fermentation. The correct answer here is option D, hydrolysis. Let's go to question number 38. A characteristic reaction of the compounds with the general formula CnH2n is what? Remember that CnH2n is the general formula for what? For the alkenes. Alkenes, okay? Okay, so the characteristic reaction for this type of, for the alkenes, okay, CnH2n is what? Esterification. Esterification reaction is the reaction that takes place between an alkanoic acid, okay, and alkanol, okay. That will give us an ester, okay, or an alkanoate and water. So this is not the case because that is the reaction between alkanol. This is for alkene, okay, alkanol and then alkanoic acid. So this is not correct. Option B, polymerization, has to do with a combination of two or more monomers, okay, smaller units, smaller molecules or compounds combining together to form a larger one that is called a polymer, okay. That is a polymerization. Of course, we have this, for instance, ethene, okay. Ethene can combine together, several monomers of ethene can combine together to form a larger molecule that is called polyethene, or what we call polythene, like the polythene bag, the nylon that we have is actually from ethene, okay, that's polythene. Okay, so this is correct, is the characteristic of. Let's look at option C, decarboxylation. Decarboxylation has to do with the removal of carbon, okay, that is decarboxy. When you see D, dehydration, removal of water. Decarboxylation, removal of carbon, okay, removing it from this. If you are removing it from this, that is not, because what we have for this alkane actually have carbon-carbon double bonds, okay. So we're looking for something that can strengthen the bonds together or remove a double bond. So but decarboxylation will not do that. Then substitution reaction will also not take place here because substitution reaction is only familiar or is common among the alkanes. That's the saturated hydrocarbons, okay, but this is unsaturated hydrocarbons, so this is not correct. So among all of this now, polymerization, option B is the correct answer. Question number 39. The pair of organic compounds that are isomers is what? Remember, isomers are compounds that have the same molecular formula but different structural formula. That means the number of carbon and hydrogen for the two compounds or the compounds that are isomers will be the same number, but the structure, in terms of structure, by the time you draw them, okay, you'll be having what? You'll be having this different structure in spatial representation of what it is. For this, you don't need to waste much time. All you need to do is look for the pair, okay, that actually have the same, so that you don't forget that the aim of the questioning or the test is to see how accurate you can be, answering questions within the shortest time, and then you are also accurate. So you have to work smart. Don't stay on the question and then you begin to show of course the examiner doesn't want to see your workings, what they want to find, what will be the end that will justify the means is going to be your answer that you pick. So option A here we have benzene, 6 is H6, okay, and then you want to do methyl benzene. This methyl already disqualified because we have benzene. This methyl added to it, that's a CH3 added to 6 is H, so it's going to increase the number of carbon and number of hydrogen, so they won't be the same. So we are looking for the ones that actually number of carbon and hydrogen will be the same. In the case is trichloromethane, we are talking about chlorine, that's Cl3, and then CH. So we have CH, Cl3, and this one is tetrachloromethane. This one is CCl4, CCl3. This one we have one H here. We have no hydrogen here. Okay, so you see that they are not isomer because the molecular formulas are not the same. Are we together? So for this one we have ethanol and propane. Ethanol is C2H5OH. Propane is C2. Okay, maybe we can just see. This one will be C2H5OH. So in other words, that is C2H6O. Propane is C3H what? That is a 6 plus 1, that's 8. Okay, so the number of carbon here is 3, number of carbon here is 2, number of hydrogen here is, so the number of carbons are not the same, so hydrogen are also not the same, so they are not isomers. For this one, both 1 in and both 2 in. This should be the answer because both, for the in, both of them are alkene. But the reason for the difference is just in the number 1 and number 2, showing that the position of the carbon-carbon double bond. For here, the double bond is in carbon 1 and carbon 2. This one is between carbon 2 and carbon 3. So in other words, what we are saying is that the number of carbon here will be 4, number of carbon here will be 4, number of hydrogen here will be 8, number of hydrogen here will be 8. But when you draw it in structures, okay, they are going to be different, but because of the position of the double bond. So among all of these options now, the correct answer here is actually option D, both 1 in and both 2 in. Do you know you can actually take practice questions with a simulated JAMB CBT past questions? All you need to do is to click on the link in the description below that takes you to the Myschool website. There, you'll be able to download the Myschool mobile app on your Android and the Myschool software on your laptops and computers. Please go ahead and start practicing. Now let's go to question number 40. A burning candle produces water and what? Burning candle produces water and what? A burning candle is an hydrocarbon, okay? And then when hydrocarbons undergo combustion reaction, because this is produces water, a burning candle, something that is burning, that means it's undergoing combustion, right? So candle is hydrocarbon, and usually when there's combustion of hydrocarbon, okay, usually the products are usually CO2, carbon dioxide, and water. Carbon dioxide and water. So in other words, they are asking you that combustion of hydrocarbon will form what? CO2 and water. So there's no need wasting time. A burning candle is an hydrocarbon. It produces water and what? They gave us one of the products already. Water and carbon dioxide. So option A says carbon dioxide. Now it would have been carbon dioxide if it is candle burning with a limited supply of air. Okay, if it's a limited supply of air, okay, we are not going to have carbon dioxide. We'll be having carbon dioxide, because what we'll be having much will be, if the air is controlled, it will be what? It will be soot. Will be forming like soot, like coal, charcoal, the black soot. Okay, that's what will be forming more in that point. So in that case, now we'll be having carbon dioxide. But in this case, it says the burning candle produces water. Just the combustion of hydrocarbon is going to form water and carbon dioxide, which is CO2. So carbon dioxide, option B, not oxygen, not hydrogen. So the correct answer actually is option B, carbon dioxide. I hope you're enjoying this content. If yes, please don't forget to click on the like button, hit on the subscribe button, and finally tap on the notification bell to keep you notified once we upload our next video. Question number 41. The gas that can best be collected by downward displacement of air. Downward displacement of air is what? Now, the way gases are collected, okay, when they are being produced in the lab, actually depends on how dense they are. Is it denser than air or lighter than air? Okay, any gas that is lighter than air means that if it is lighter than air, it means the gas is going to be on top and then the air will be underneath. Okay, which means the air is actually denser or than the gas. But any gas that is denser than air will be underneath the air, while the air will be above that gas. So the type of delivery, the type of displacement, whether it is upward displacement or downward displacement, depends on how densely that gas is. Now the question is chlorine. Option A says chlorine. Which one among these now can be collected by downward displacement? Chlorine gas is denser than air. Chlorine gas is denser than air. So if it is denser than air, it means that it's going to be underneath while air will be above. So you cannot collect that one by downward delivery. If you are collecting by downward delivery, it means that the tube or the hose that will be collected, the jar will be above, okay, so that you can take it up, or it will be downward. Okay, the jar will be downward so that the hose will be going down because it is underneath. Okay, but in the case of chlorine, chlorine is actually denser than air, so it is underneath. Okay, while air is above. So to take this one now, you need upward displacement of air. Okay, is what will make us produce, so not the downward chlorine. Then look at sulfur dioxide. Sulfur dioxide, SO2, is also denser than air. Okay, so it's going to be underneath while air will be above that. So you can't take it by downward delivery. It has to be by upward displacement. Okay, you can't take it by downward displacement, it's upward displacement. So option C is ammonia, NH3. Ammonia is lighter. Yes, ammonia is lighter than air. It's lighter than air because it's lighter than air. So ammonia is going to be above while air will be underneath. So for that, you can actually take that ammonia, you can deliver it, you can collect that ammonia by downward displacement of air. If you displace air downwardly, then you'll be able to get and collect your ammonia because it's above it. And then for carbon dioxide is also denser than air, so it's going to be underneath while air is above. So you will need an upward displacement of air for this. So option A, upward displacement. Option B, upward displacement. Option D, upward displacement of air. But option C, because ammonia is lighter than air, is actually the correct answer. Option C is the correct answer. Now let's move on to question number 42. Which of the following metals burn with brick red flame? You know, when metals burn in flame, they produce different colors. That's how you can distinguish them on what they do. Option A says, don't forget, brick red flame. Option A, when you burn lead, okay, PB, that's lead. If you burn it in flame, okay, you burn it, okay, with it, what you are going to have, the kind of flame you have there is always a grayish white kind of flame. Grayish white, yes. It has a gray like whitish sky. Okay, so that's what we have here. Option B, calcium. Calcium, if you have metal, calcium metal burning, you have a brick red flame. That's what we form for calcium. For sodium, sodium is usually a golden yellow color. Yes, that's the color for sodium metal, golden yellow color. And then option D, magnesium. Magnesium has a white also, but the white is different from this one. This one's white is a bright, dazzling, dazzling kind of a color, white, okay, flame that we have for magnesium and this. So option C is a yellow, golden yellow color. Option this is grayish white, and this one is grayish white, and this is a bright white. But option B is the one that has the brick red flame. So option B, calcium, is the correct answer. Question number 43. Which of the following represents hybridization in ethyne? Hybridization. What is hybridization? Hybridization has to do with, addition or mixing of together of orbitals. When we talk of orbitals, we have the s orbital, we have the p orbital, we have the d orbital, okay, we have the f, and so on. So s, p, d, f. Those are the orbitals that we have commonly. So when you have maybe one s mixing together with a p orbital or with d or with f and so on, we say we have hybridization. So which type do we have in ethyne? Okay, I will just use the 3 carbon 2, okay, for the 3 hydrocarbons to explain this concept. So let's move to the board now to see what we have. If we have ethane, we have ethane, we have ethyne. Okay, don't forget that ethane is a C2H6. This is C2H4, and then this is C2H2. Yeah, it has 2N-2. So if you draw for this, because this for the hybridization is going to determine the kind of shape, okay, and energy that compound actually has. So we have 2 carbon atoms here with hydrogen. 1, 2, 3. 1, 2, 3. For this we have 2 carbon, so that's double bond. We have hydrogen, 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 hydrogen. Then for this we have 2 carbon, that means triple bond carbon atom, 1 hydrogen here, 1 hydrogen here. To make it easier and simpler, okay, we are talking about the shape now. Now, anywhere you see the carbon atom, between this carbon atom and carbon atom, we have s orbital, okay, taking place there. So we just use s to represent that. Then we see for each of this carbon atom now, okay, how many hydrogen do we have here? 1, 2, 3. So that one should be for our p, okay, orbital. So we have 1 carbon, that's your s, okay, then we have 3 hydrogen, so that can be sp3. So let the p represent the hydrogen. This is the simpler way, okay, to explain this. sp3. Now let's look at this one. We have, for this carbon, we have 1, so for where we see carbon, let's have s orbital there, okay. Then we have for the hydrogen we have p. How many hydrogens do we have here? We have 2 hydrogens, okay, for each of these. That's sp2. Then in this case, how many we have carbon? For this carbon we have 1, so let it be what? s orbital. And then how many hydrogen do we have attached to this carbon? Just one, so that is sp. So this is our ethyne actually that was asked. So the hybridization that we have there is sp. So let's move to the screen. Which of the following represents hybridization in ethyne? Okay, sp2, no. sp2d, sp3, of course, no. This one would have been if it were in ethane. Okay, this would have been the answer if it were in ethane, ethene. Okay, and then this would have been the answer if it were ethyne. And of course, that is the answer because we are talking about hybridization in ethyne. So it is sp hybridization that we have. So the correct answer is option D. Now question number 44. C12H22O11 plus H2SO4. Okay, this reaction is actually referred to as a dehydration reaction. Okay, dehydration reaction. The reason being that this is sugar here. Okay, it could be your sucrose, sugar we take. Okay, if you react it with concentrated H2SO4, okay, what happens is that it's going to dehydrate and remove water from this. That's why you see the product we have, the water, 11 moles of water is removed. A whole 11, moles of water is removed from this. So water is dehydrated, it's removed from this. So of course, it shows that it is dehydrated. And then this carbon that you have here, you can see it, it's a charcoal. If you add concentrated H2SO4, you can try it. If you had concentration, but don't do it on your own, it should be under the supervision of a teacher. Add concentrated H2SO4 to sugar, okay, in a beaker, and then you discover that within seconds, everything will just turn into charcoal. You will see it black. That's the carbon that you have here because the water content that is inside of that sugar has been removed, and then you will have H2SO4 still form maybe under the container. You still have it. So in the reaction above, tetazosulfate 6 acid functions as I've already said it's going to function as a dehydrating agent because you can see that water was actually removed. When we say dehydrate, when you dehydrate, that means water has been removed. Humans dehydrate. Okay, when you need more water, water is taken. So the H2SO4 is acting as a dehydrating agent here because it removed the molecule of water from inside it to form carbon, okay, that is black that you have here. It's actually a black one. So the answer is not oxidizing agent. Yes, H2SO4 also acts as oxidizing agent. It can also act as a reducing agent, but depending on the kind of reaction it is undergoing. But in this case now, it is removing water from this, 11 moles of water from this sugar. So it is acting as a dehydrating agent, not a catalyst, not a reducing agent, not oxidizing agent, but a dehydrating agent. So the correct answer is option A. If you have any question bothering you, please feel free to ask. You can do that by clicking on the link in the description below that takes you to the Myschool website. There, you'll be able to ask your questions and solutions will be provided to you within the short period of time. Now let's go to question number 45. When sodium reacts with water, the resulting solution is what? Don't forget that sodium is actually a metal, a group 1 element, okay? And usually when metals react with water, they usually form alkaline. So that is why they are referred to as, group 1 elements are referred to as alkali metals, okay? Alkali metals. And group 2 elements, when they react with water, they actually form what we call alkaline earth metals, okay? So, but this is a sodium, okay, reacting with water here to form what usually is going to form an alkaline, which is sodium hydroxide and hydrogen gas. Let's move to the board and see what happens here. We have sodium metal, of course that's solid, reacting with water, H2O, that's liquid. What happens? We have sodium here be formed, then one oxygen here, mole of oxygen, and one hydrogen here. Then we have hydrogen gas will be formed. So this is aqueous. So we can balance the equation here. This takes 2, that's 4, yeah, because this is 2 here, so that sodium is 2 here, sodium is 2, sodium is 2 here, hydrogen is 4 here, hydrogen is 2 plus 2, that's 4, oxygen is 2 here, oxygen is 2 here, okay? I think the equation is balanced now. So this is an alkaline. Let's move back to the screen and see what we have. When sodium reacts with water, the resulting solution is weakly acidic. It's not weakly acidic because sodium hydroxide is not and acid is a base, okay, and alkali. Then we have neutral. It is not neutral because sodium hydroxide is not acidic, it's not acidic. And then we have alkaline. Sodium hydroxide, of course, is an alkaline solution. So the correct answer is option D. Do you have better explanations to all of the questions we'll be solving? Please do well to share with us. You can do that by going to the comment section, indicate the question number, and then you will provide the solution that you want to share with us. Question number 46. Which of the following gases contains the least number of atoms at STP, standard temperature and pressure? Which of the following gases contains the least number of atoms at STP? So we are going to the board now and we will take them one after the other. The list, don't forget. Option A says 1 mole of butane. 1 mole of butane, okay? So that is 1 mole of butane, that is 1 times. Butane is actually CH4, okay? So we have, that's 1. So we have carbon is 1. Okay, plus hydrogen, we have 4 hydrogen, 4 atoms of hydrogen here. So plus 4, that is 5, okay, atoms. The option B says 3 mole of ozone. 3 mole, okay, of ozone. Of course, you know that ozone is 3 moles, 3 atoms of oxygen, okay, actually gives ozone. So we have 3 moles of ozone. Ozone is O3, okay, so that would be 3. Oxygen, we have 3 here. So this is 3 times 3, okay, that gives us 9. So we have 9 atoms, okay, here. For this we have 5 atoms. Let's look at the third one. Option C, 4 mole of chlorine. 4 moles, of course, moles of chlorine. Okay, you know that chlorine is diatomic, okay, chlorine is Cl2, okay, but we have 4 here, okay, so we have 4 of that. So 4 times this 2, okay, what do we have? That is 8. So we have 8 moles, okay, present there. And the last one, option D, 7 mole of argon. 7 moles of argon. Okay, argon is just mono, like this. So we have 7 here. Okay, so that would be 7 times, of course, 1. So that gives us 7 moles. Okay, so we have 1 mole of butane. Oh, sorry, let's correct this. Butane is actually, this is methane. Butane is actually C4, meant to be. That's C4H10, yes. C4H10, that's what butane is. Butane, that CH4 was actually for methane, okay? Butane is C4H10. So that is a 4 of this plus, this is 10, plus 10. So that gives us 14 atoms, okay? So among all of these ones now, 1 mole of butane has 14 atoms. 3 moles has 9 atoms. 4 moles of chlorine has 8 atoms, because we are asked that which one contains the least number of atoms, okay? 7 atoms, okay, actually there. So among all of this now, the one that has the least is actually 7, okay? So which is 7 moles of argon. So let's go back to the screen to see what we have there. 7 moles of argon, not A, B, C, D, D. So 7 moles of argon. So this is what we have. So option D actually has the least number of atoms at standard temperature and pressure, okay? So which means option D is the correct answer. Question number 47. We have a graph here and we're told to use the graph above to answer this question, okay? If the gas is cooled, at what temperature will it start to condense? At what temperature? So we have, from this point, we have temperature. On the y-axis, we have time in minutes. On the x-axis, okay? We have 0 to 1, 1 to 2, 3, 4, 5, 6, 7, and 8. And on this point, the y-axis, we have 0 to 100, 200, 300. So from here, from this point now, origin now, to this point, we have solid here, okay? From this point to this point, what we have here is solid. Then it continued, and then eventually it moved up again to liquid, okay? And then from this point it continued, it is uniform, the temperature was constant until eventually, and the time at which it takes place is constant until what? It changes to what? To vapor. So now from this point, now the question says that at what temperature will it start to condense? Of course, condensation has to do with when the liquid is already at the, yes, condensed. We have the liquid again turning from from gaseous, from gas to what? To liquid. That's when we talk about condensation. The gas substance or molecule is turning back into liquid. And then when we talk about gas, we are talking about vapor. Okay, so when with the vapor, it eventually begins to, so it's at the point where the temperature begins to drop. There's a point where the temperature of that gas gets cooled. Okay, if it is when the cooling takes place, that's where condensation begins to take place. So the gas needs to get cooled first before it begins to what? Condense. If you look at the graph here, we have vapor here. You see it's coming down from this time 7 to 6. Okay, that's the cooling is already taking place. So once it gets cooled at this point now, that is where condensation takes place. So it continues moving that way. Okay, at this point, that's where the point of condensation. So you can just extrapolate this, straighten it like this, straight to this point. Okay, if you take this way, take it this way, because that's this point now. That's where the condensation takes place. That's where the vapor, the gas is turning into liquid. Okay, it's coming here and then it gets to this point. So we trace it down because we asked at what temperature. So you take it to this place. This point is actually, okay, this is 100 here. From here to this middle, that will be 50. From here to here, that's another 50. So this is 50. 100 to here, that's 150. So which means each of the boxes is actually taking about that. So from here to here is 150 degrees around that. So let's look at the options we have. So this at this temperature, that's why we have that. Option A says 1 to 5 degrees Celsius, which is somewhere around here. Okay, no. 150 degrees Celsius, which is here. That's this point here. And then we have 175, 250, not that. So the correct answer here is 150 degrees Celsius. Option B is the correct answer. Now let's move over to question number 48. We still have the same graph that we had in the previous question. So use the graph above to answer this question. How long does it take? That's time, okay? How long does it take all the solid to melt? All the solid to melt. What's the process? That is melting, okay? When solid substances or solid matter, changes states to what? To liquid, okay? We say that is melting. So how long does it take? So let's go back to our graph. We are talking about how long. Look at the solid here, from here to here, okay? It's still solid. It's still solid as at this point. It was when it got to this point, the melting actually what? Started, okay? And then at this point, it's turned into liquid, okay? So melting has taken place between here and this point. So what we are looking at is we are looking at from here now, we take it, it's still solid from this point. So it takes place because it says for how long does it take all the solid to melt. So it's actually started melting here, okay? It continued here, it's still solid to this point, still moving. So the melting continued until it got to this point, okay, where the liquid actually stops. So if you trace that down, this point here is where it actually happens. So from here to here, that is what we have. So if you check it now, we have that's 1, 2, 3. So this here is 0.5. So this is 2.5. So 2.5 at this point here. That's what we have here. So it's going to take 2.5 minutes, okay, for all of the solid to actually melt. So option 2.5 minutes. Option A is the correct answer. 2.5 minutes. Question 49. The diagram above represents the formation of, don't bother about the diagram, okay, I've redrawn it on the board, we are going to see it now. The diagram above represents the formation of what? Let's move on to the board. So we see what we have. So this is, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, okay, of course. If you know your multiplication, your periodic table very well, okay, 17. So that tells you, at least that will give you a clue that this is a chlorine atom, okay? And then you count this again, it's the same 17. The total number of electrons we have is still 17, okay? 17, 17. And then 2 of the atoms of chlorine, of this and this, actually combine together to form a singular one. You can see it here. So now in the outermost electron, in the outermost shell, we have 1, 2, 3, 4, 5, 6, 7. This one chlorine atom, or this particular atom, let's assume we don't know what element it is, okay, actually needs one more, okay, to complete its octet rule, okay. The same thing for this. This has 1, 2, 3, 4, 5, 6. This one also needs one more to complete that. So both of them now, they need one, this one needs one, this one also needs one. It would have been metallic, okay, if it were just joined together without any transfer of electrons, okay. Option A, metallic bond. Option B says is an electrovalent bond. And you know, electrovalent bond has to do with ionic bonding, okay. That one involves what? Transfer of electrons, usually from the metal to the non-metal, okay. But in this case now, there's no transfer of electron because two of them, this one needs one, this one needs one. This one cannot transfer its own to this. If it does, it will be deficient of 2 electrons, okay. Then this one will not be satisfied. But don't forget, the essence of the bonding is actually for both of them to be what? To be okay, to be satisfied, and then fulfilling the octet rule that the outside mode they should have completely filled. And so once they now say, okay, this chlorine atom comes with this one, and then they combine together, and then you can see what happens here after bonding. This one now brought its own, this one also brought its one, and then they share. So when they share, this one now becomes chlorine, this one becomes chlorine. So both of them will now form chlorine molecule, okay. And then you know that it is in molecules, okay, are formed in covalent bonding. If you look at the options, this one now we have this one, of course, this one brought its own, this one brought its own. They shared the electrons, so they're sharing of electrons. Let's go back to the screen so we can see what happens here. Like I said earlier on, it's not metallic bond because we don't have electrons that are mobile. We don't have electrons, delocalized electrons around, okay, that one, and they're not compactly put together, so it's not metallic bond. Electrovalent bond is not electrovalent bonding, the reason being that it is not ionic. There's no transfer of electrons between those atoms. What we saw there was just what? Sharing of electrons. So by elimination method, option A and option B are stricken off. So we have option C and D left because both of them actually look alike. Option C is a covalent bond. Option D is a coordinate covalent bond. So this is a type of covalent bond also that is. So because it is two of them that involves sharing of electron. What we saw there was actually sharing of electron. So this one involves sharing of electron. This also involves sharing of electron. But this is ordinary covalent bond because one of the chlorine atom brought one electron, the other chlorine atom brought one electron. So both of them donated and contributed the electrons that were shared between them. So that means it is 50-50 kind of thing, okay? That is ordinary covalent bond. But for coordinate covalent bond, which is also called dative bonding, that one involves the electrons that are shared, the lone pair of electrons shared, it will be donated by one of the participating atom. If it was just one among those two that donated the 2 electrons that were shared, then it would have been coordinate covalent. But it was 2 of them that actually contributed the 2 electrons that they shared, each of them bringing one, and they shared. So that is ordinary covalent bonding. So which means that option C, a covalent bond, was actually what happened in this case. Now, so the correct answer is option C. Question number 50. Use the solubility curves below or above, as we have it here, to answer the question. If 1 dm cube of a saturated solution of L, that's the salt of L, at 60 degrees Celsius is cooled to 25 degrees Celsius, what amount in mole will separate out? What amount in mole will separate out? So all we need to do here is that we have, of course, this is a solubility curve. It's usually a curve of solubility plotted against the temperature, okay? So this is temperature, this is your what? Solubility. There was a question they asked that solubility curve, solubility is always plotted against what? Temperature, and so it's always against temperature. So this is the temperature. We have from 10, 20, 30, 40, 50, 60, 70, and so on to 100. So we look out for, there are 2, slopes here. There are 2 curves here. We have curve. This is the first curve here, which is L, and then we have this one that is what? That is K. Our area of concentration is not with K because we're asked for what? For L at 60 degrees. So this is L. So we are only going to take cognizance, put this into cognizance. This curve is what we are looking at eventually. So, but we're told that it was getting cooled from 60 degrees Celsius to 25 degrees Celsius. So first, we will have our 60 degrees. This is the 60 degrees here. We'll take it from here. We'll take it to the point where it intercepts the curve. Okay, that's 60 degrees. and then we do what? We extrapolate. We take it straight up to this point. Okay, when we take it to that point, then we get the value for that. So from what I see here now, this is 10, here is 20. So here, of course, this is 2.0, sorry, and then this is 1.0 because this is 3.0. So it is 1.0, 2.0, 3.0. So at this point now, for this one we have at 60 degrees, we trace it here. So this gives us 1.5. So this is 1.5. So that means at 60 degrees, okay, the solubility was 1.50. Of course, you can have it as mole per dm cube. And then let's check the other temperature is at 25 degrees, at 60, at 25. At 25 degrees, so we come here again and trace it. This is 20, this is 30, so in between is 25. So we trace it again to this curve. Don't forget, it's this curve of L we are looking at now. We trace it here and then we interpolate, then we move it this place, then we have it here. So what we have here actually is, we have 0 here, 1 to here, 1, 2, 3, 4. We have about 4 different boxes inside of that, okay? So that would be 1, 2, 3, okay? So that means each of them is actually 0.25, 0.25, 0.50, 0.75, and 1.0. So this is 0.75. So that means at 25 degrees Celsius, solubility is 0.75 mole per dm cube. So the question says, what amount in mole will separate out? Let's move over to the board now and see what to do about that. So already we said that at 60 degrees Celsius, solubility was 1.50 mole per dm cube, and then at 25 degrees Celsius, solubility was 0.75 mole per dm cube. So first we need to find the difference in this solubility of the two of them. So 1.5 minus 0.75 gives us, that is 5, 15, that's 14 minus that is 7. And then we have 0. Okay, that's 0.75 mole per dm cube. So in other words now, this is our solubility. Okay, we need to find the difference between them. Solubility is 0.75 mole per dm cube. So the question says that what amount in mole will separate out? What amount in mole will separate out? We have already calculated that 1.50 minus 0.75 actually gave us 0.75. Okay, so let's move back to the board. Let's move back to the screen and see what we have there. So use solubility curve to answer. So if 1 dm cube of a saturated solution of L at 60 degrees is cooled to 25 degrees Celsius, what amount in mole will separate out? So we had 0.75 mole per dm cube. It means that 0.75 mole will be dissolved in 1 dm cube, because they said in 1 dm cube what amount will be separated. So 0.75 mole in 1 dm cube. So the option here is not this, it is option A, 0.75 mole. So the correct answer here, or the amount in mole, okay, that will separate out will be 0.75 mole. Option A is the correct answer. I hope you enjoyed this content. If yes, please don't forget to click on the like button, hit on the subscribe button, and finally tap the notification bell to keep you notified once we upload our next video.